Hello, good afternoon. My name is Desai Daniel John, and today I'll be talking about an LSTM model, which is the long short term memory neural networking model that is commonly used when making time series forecasts. Um, here, I worked with the J17 dataset. I also made use of the St. Marcos dataset and the Comau dataset. If you can remember from my last video, the J17 dataset was about the water level elevation. The San Marcos was about the discharge, and the Comauto was about discharge in different sites. Um, from the beginning of of my code here, I imported all the libraries that I needed for this to build this model. Then I set my parts, and then I imported my J17 data series, which I saved in DF, which is what we have over here. This is the water level elevation that we collected from the site, and here I had to block this code out because I tried using it initially, but it didn't work as well as I thought it was going to. Maybe I made a mistake somewhere. But I was able to split the data set into training, testing, and validation later on. I had to convert the data set into an NumPy array and also rescale it, which is what we have here. And then we had a look back of I had to make use of a look back of 50, which is it takes 50 times case to for when the model is running, so it considers a 50-day period for when it's training. Here we're creating input and an output data set, and then I was able from X, which was my input array, I split into training and validation, and training and testing. Then I further split the training into another training and validation, which I use in building my hyperparameters and setting my hyperparameters like weight and all not. Then I reshaped this again. And then I defined the LSTM model. Well, this LSTM model has two categories, which is it has the LSTM layer, and then it has a dense layer, which is for the output. The LSTM layer is a type of recurrent neural networking layer that is commonly used for time series forecasting problems. The LSTM layer uses a combination of memory cells, gates, and inputs to maintain and update a cell state, which allows it to capture long-term dependencies and the time series data. The dense layer is a fully connected layer that outputs a single value, which is the predicted value for the next step in the time series. So after doing that, for the purpose of this video, I'll be training the model for just 10 epochs, so it doesn't take longer time to run. You can make a training for longer time of epochs. You can increase the epochs to 50, 100, whatever you want. It's really doesn't matter. You just have to be careful not to overfit the model. So I trained the model for just 10 epochs, and after that I was able to make some predictions. And in a short while, I will show you a plot of what these predictions are. Here this is I was also able to calculate the root mean square error, which as you can see here is 1.9. I had to import a new library to make this plot so that we can really visualize what the you can really have a visual picture of what the predicted values and the testing values are in the time series data. So after making this plot, let me go here so we can see the plot clearly. Let me increase this for you. So here we have our plot. The orange line shows the test data set. These are the actual values from the J17 data set. And then the blue line represents the predicted values. We can see there's a little bit of variation because there's no neural network model that can get that can make 100% that is 100% accurate. If it happens to be 100% accurate, that means the model is just has been overfitted and it's just cramming values. So here we can see, but the predicted values and the actual time, the predicted values and actual test values have the same, more or less the same trend. And this is how it goes from the first from the initial date. It goes the same way all the way up to the last date in the testing data set. Um, so I was able to also do this for the St. Marcus and also for for the coma. So let us take a look at what the St. Marcus looks like. Let me close this up a bit. So for the St. Marcus, it was basically the same code. It just this is the same code that I ran. I set my working directory, import the data frame. One thing I did notice when I was working with this St. Marcus, let me take it back to here so we can see what I'm doing in ActionSense. One thing I did notice was that when I started the time series analysis, I had the dates backwards, so I had to change them. I had to arrange clean up the dates a bit, and I couldn't work with very long data sets because it had my time frozen. So I had to cut my data set from 2017 to 2023 was the data set that I used. I did the same conversions that I did with the previous data sets, and I also set the look back which I needed when I did create the input and the output data set. I was also able to split it into training data set, validation and testing data set, and which I also had to reshape to match the LSTM input shape. Then um, I also created defined the architect of the model. As you can see, the optimizer that I use even in the time series data set is the same optimizer that I use here. The optimizer is Adam, and then I was able to train the model too for 10 epoch. Let me increase this just for the sake of it. Let me make it 20 epochs, and we'll see how that goes. And then we can train it for 20 epochs, and it's just gonna take a longer time to run, but it really doesn't make any much difference. It might give us a more accurate result. But we just need to be careful so that we don't overfit the model. Else the model is just gonna be recalling values that it's just gonna cram the values and just recall that for us. Um, After this is the epochs are almost done. So here I was able to make the prediction. Let me go ahead and highlight that. Okay, so our training is done. Here I'm able to make predictions, and in a short while we'll also be able to visualize the predictions. Let us see what the root mean square error of the model is. And I imported matplots for that, and then I'm able to do this and see how the predictions that the model made um, and the actual testing values are. You can see there's a little bit of variation here and there, but overall it has the same trend. Due to loss, we cannot exactly get due to losses in errors, we cannot exactly get the same values, but we all see that it has a nice trend. So the same thing too goes for the commodity set. This I'm just gonna run one since I've already gone over the code before. This one I did for 10 epochs, and I just want to see what the I'm gonna run it up to the test up to from beginning to end and just see how it goes. And at the end of the day, it's almost done. So this is the plot of the prediction that he made, which is also quite similar to what we have in the testing data set. And this will be the end of my video. If you want to take a look at the code, you can go to my GitHub page. Desei is actually named DESEYI. And you can go to my GitHub page, and you will have this code that it's an open code, so you can also take a look at the code and try using it for your own time series um, predictions. Thank you very much.